Hi everyone, welcome to the first of 3 videos going through some past exam questions on electrode potentials. The first question we've got here is one that's pretty typical of this sort of question. We've got a table with various different half equations in equilibria, and we've got their electrode potentials down the side here. It's got a bit of blurb here about what electrical constants are, and they're very useful and whatever. But let's go straight to the question here. So it says, an electrochemical cell can be made based on redox systems 2 and 4. Draw a labelled diagram to show how this cell can be set up in the laboratory. Okay, so what have we got? Redox system 2, we've got Fe3 plus in equilibrium with Fe2 plus, and number 4 is Ag plus ions and silver as a solid. Okay, so what we're going to need is a beaker over here, and we're going to need an electrode. And we're going to need another beaker over here, and that's going to have an electrode in it as well, and there's going to be some sort of solution in each of these. Those electrodes are going to be connected up. We want a voltmeter so that we can measure the voltage. Okay. And so then let's talk about what's going on. We've got Fe3 plus and Fe2 plus. Use the state symbols here, right? This is aqueous and this is also aqueous. Okay, so that's going to be in here. Okay, let's have this solution. And this needs to contain Fe3 plus and Fe2 plus. Okay. So if we've got both Fe3 plus and Fe2 plus in the solution, we don't want an electrode made out of iron. Okay, because then we'd have iron in 3 different oxidation states. And we wouldn't just get this reaction happening, we'd also get an equilibrium between iron the solid and Fe3 plus and iron the solid and Fe2 plus. So this is going to have to be an electrode that's not made of iron. It's going to have to be a platinum electrode. Okay. Platinum's unreactive, so that's why we want to use that. Okay. On the other side, the other redox system is number 4, so that's Ag plus aqueous and silver as a solid. Okay, so this solution here is going to be Ag plus aqueous. And this time we've only got 1 iron in the solution, so we are going to have silver solid as the electrode. And then we've just got the 2 oxidation states of silver. Okay, so we've got our 2 half cells. We've got a voltmeter that's linking them up, but this is not a complete circuit. Okay, we've got electrons can flow through the wire from one electrode to the other, but then how do they complete the circuit? Okay, what we need finally is a salt bridge linking the 2 together. Okay, and remember the salt bridge is usually just a piece of filter paper that's been soaked in a solution. It's usually potassium nitrate is pretty common, just because then those ions don't really react with anything to make precipitates. They then just dissolve back into the solution, and this allows ions to flow if necessary, and stop charge building up, which would prevent the cell from working. So don't forget your salt bridge. You don't need any sort of detail. You can see I'm not any sort of artist here, but as long as you've labelled it, then it's clear what everything is. Okay, it doesn't actually need to be a good drawing as long as you've labelled it. Okay, so moving on from there, we've then got a few little questions about this cell. So state the charge carriers that transfer current through the wire and then through the solution. And actually we've kind of already mentioned this, that through the wire, what's going to be carrying charge is going to be electrons moving through the wire, whereas through the solution we're going to have ions moving. Okay, and that's what's going to carry the charge in the solution. Number 3 then says write down the overall cell reaction. Okay, so we're going to have to go back to our electrode potentials here. So we've got redox system 2 and 4, haven't we? So this iron half equation, equilibrium, its electrode potential is plus 0.77. The silver is plus 0.34. Okay, so remember the sort of golden rule with electrode potentials is whichever one is the most positive, that is going to be the reduction half equation, and whichever one is more negative, or less positive at least, that's going to be the oxidation. Okay, so out of the 2, this Fe3 plus 1, that's the more positive one, so that's going to be a reduction. So that's actually going to be as it's written from left to right. It's going to gain electrons. So we're going to have Fe3 plus on the left and Fe2 plus on the right of our equation. This silver half equation then, because it's the less positive one, this must be reacting the opposite way round. Okay, so when we come to write this equation, it's going to be Fe3 plus reacting with Ag solid. There's only one mark. It doesn't mention state symbols, so we don't need to worry about state symbols here unless it specifically tells us in the question, which it doesn't. So those two are going to react together, and we're going to get Fe2 plus as the product and Ag plus. When we're writing these equations, it's important that when we combine these two half equations together, that the electrons cancel out. So going this way, we've got one electron being gained, and then remember we're doing this equation backwards because it's the least positive one, so we'd have one electron being lost. Okay, so the electrons would cancel out here. And we can double check by checking that the charges are balanced. I've got a 3 plus charge here, and overall a 3 plus charge on that side, so we're okay. Then wants us to write down the cell potential. And notice here the instructions, I think is worth looking at. It just says write down. It's not calculate, or this is giving us a clue that this should be easy, right? We're not going to have to do anything particularly difficult here. So write down the cell potential. Well, if these are my two electrode potentials, 0.77 and 0.34, then the cell potential is the difference between the two, isn't it? It's the potential difference. So it'll be 0.77 minus 0.34. So it would be 0.43 volts. Okay. Okay, and then moving on, select from table 4.1 a species that will oxidize Fe2 plus to Fe3 plus. Okay, so let's have a look here. If we want to oxidize Fe2 plus into Fe3 plus, then this half equation equilibrium is going to have to be happening backwards. That reaction's happening backwards, it must be because this is the least positive out of the two electrode potentials. And remember, the more positive electrode potential is the one that reacts forwards as a reduction. So we need something that's going to have a more positive electrode potential than plus 0.77. So we've got a few options. We've got two options here. We could either choose this one or we could choose this one. Okay. What's the reactant going to be? What's the species going to be? So in this equation, it would be the chlorine. This reaction would be happening this way. So it would be chlorine, and that reaction would be happening backwards. If I was to choose this one, then I would have to have O2 and H+. Okay, we need to write down both of these. Okay, you can't just have one. That combination would react with Fe2+. But let's keep it simple. Let's just go with the chlorine. That's the easier one. Okay. And then a species which reduces Fe3+ to Fe2+. So that we're looking for the opposite of what we've just done, but does not reduce Ag+ to Ag. Okay. So if it oxidizes Fe2+ to Fe3+, we said we wanted something more positive than plus 0.77. So here for reducing it, we want something less positive than plus 0.77. So it could be this one, it could be this one, it could be this one, it could be that one. But it does not reduce Ag+ to Ag. So Ag+ would not be reduced. So this would not be going from left to right. So that would be going from right to left, and that would happen if this was the less positive one. So we need one that's in between these two. Does that make sense? If it's going to reduce one but not the other, what we're looking for is a value that's in between these two. So in between 0.77 and 0.34. In which case, obviously it can't be that one, because that's the value, and it can't be these. It's going to have to be this bottom one. That's the only one that is in between these two values. Okay. So it's going to be this one, but then we need to be really careful. It's asking us for the species. So a species which will reduce Fe3+. So something that would react with Fe3+. In other words, this equation would be going forwards, and the other equation would be going backwards. So the species we're going to have to choose is the I- here, not I2. Okay, we're going to have to be very careful because we want that reaction to happen that way, for the Fe3+ to be reduced, which means this reaction is going to have to be backwards. So we're going to start with the I-. So make sure you're being specific with those things. Don't copy the whole equation out. You're picking one species. Okay, moving on. As I said before, these questions do kind of all look the same after a while. Here we've got another table of equilibria and electrode potentials. So the more you do these, the more they kind of start to look the same. And it wants us to define the term standard electrode potential and include all the standard conditions. Okay. So the standard electrode potential, this is just a definition that you need to remember. Okay. It's a bit of an odd one, but remember we're going to use this term EMF, and we can actually write it like that. Remember, EMF stands for electromotive force. So it's basically the force that makes the electrons move. Okay. So the standard electrode potential is the EMF. We can say of an electrode compared to the standard hydrogen half cell. And this is a sort of a theme in chemistry that we've seen before, where there's a lot of chemical measurements that are not made just on their own, they're made relative to something else. And that's the same with all these electrode potentials. They're all made relative to the standard hydrogen half cell. And actually, if you go back to the previous question, you'll see this is our standard hydrogen half cell. You'll see that's why it's got an electrode potential of exactly 0. Okay. Standard hydrogen half cell is your H+ ions in solution and hydrogen gas. And again, you'd have a platinum electrode again, like we did with this one. So that's your definition. It's the force that makes electrons move for this electrode compared to the standard hydrogen half cell. And it says include all the standard conditions. So standard conditions would be 298 Kelvin or 25 degrees, doesn't matter. We'd have normal atmospheric pressure, so it'd be 100 kilopascals. Or you could say 101. They will let you get away with either. Let's not go into the story of why you can say either of those. It's a story for another day. Or you could just say 1 atmosphere. And then the other thing is we need solutions to be 1 mole per decimeter cubed. And that does matter because we're going to have lots of solutions in all these half cells. Okay, the student then sets up a standard cell based on Redox systems 3 and 4. Draw a labeled diagram to show how they could set this up, right? So it's very similar to the question we saw earlier on, right? Deliberately have left this in to show you, look, the same questions come up again and again. So again, we're going to have some sort of beaker over here with some sort of electrode, and we're going to have some sort of beaker over here with some sort of electrode in it, with some sort of solution in each of those. They're going to be joined up by a voltmeter so that we can measure the voltage, and we're going to have a salt bridge like we had before. So we can draw all of that. And then we just need to look at, right, what are these two actual Redox systems 3 and 4. So Redox system 3, we've got V3 plus aqueous and V2 plus aqueous. So you can see this is very similar to what we had before. We've got 2 different ions, both in solution. So let's label this up. This solution is going to have V3 plus and V2 plus in it. And therefore, if we've got 2 different ions of vanadium, we don't want to use a vanadium electrode. We're going to have to use a platinum electrode. Again, because we don't want 3 different oxidation states of vanadium. Okay. And then Redox system 4 is this one with copper 2 plus and copper as a solid. So again, it's very similar to the last one. Again, the last one had one with a platinum electrode, and then this one doesn't need a platinum electrode, does it? We can just have Cu2 plus in the solution and solid copper as the electrode here. Okay. Student sets up a cell. What else did it say? Draw a label diagram. Show how they should set this up. To measure the standard cell potential. Well, I think perhaps if they're saying we're trying to measure the standard cell potential, perhaps we ought to talk about the standard conditions here, although we have mentioned it here. But let's say that this would need to be 1 mole per decimeter cubed solution of copper 2 plus, and this would need to be 1 mole per decimeter cubed of each of these. Okay. On your diagram, show the charge carriers in the circuit joining the half cells. Again, well, this is the question we had earlier on, isn't it? The charge carriers, that's this question. Okay, so the charge carriers here, let's say charge carriers in here are the ions. So that would be in the solutions and also in the salt bridge. And in the wire, the charge carriers would be electrons. Okay. And then finally, it then says label the signs of the electrodes. Okay, so this, all we need to do, this is actually really straightforward. We just need to look at the electrode potentials. Okay, we don't actually have to think about this at all. The vanadium one is minus 0.26. The copper one is plus 0.34. So therefore, that's the negative electrode. That's the positive electrode. Okay, I'm kind of surprised that they actually make a question out of this. So this is the positive one with the copper, and this is the negative one with the vanadium, because that's the way round the values are. Okay, so we don't really need to think about that too much. Okay, finally, last couple of questions. What is the standard cell potential? So again, we did this earlier. This is just work out the difference between the two. So the difference between these two is going to be plus 0.34 minus 0.26. Okay, so work that out. Just, I can do that in my head, but let's do it on the calculator so we don't make a stupid mistake. So we end up with 0.6. And then finally, right, what have we got here? Explain what is meant by the terms oxidizing agent and reducing agent. Illustrate your answer by predicting reactions from redox systems 1 to 6, in which chromium behaves as an oxidizing agent and as a reducing agent. Okay. Include equations that explain why you've made your predictions. And this is a 6-mark question. Okay, so we've got a fair bit to do here. Okay, so let's start with these definitions then. So an oxidizing agent is something that oxidizes something else. Okay, so if something else is oxidized, that something else must have lost electrons. So therefore, the oxidizing agent is something that gains electrons. Okay, so an oxidizing agent gains electrons in a redox reaction. And that's all we need. A reducing agent is something that loses electrons. Okay, the reducing agent loses electrons, so whatever it's reacting with gains electrons and is therefore reduced. Okay. Okay, so that's our definitions. Then we want to illustrate our answer by predicting reactions in which Cr3+ is an oxidizing agent and as a reducing agent. So we need one equation where Cr3+ is gaining electrons and one equation where Cr3+ is losing electrons. Okay. So let's go back to our electrode potentials. And straight away we've got this one. Look, here we go. Cr3+ gains electrons to go to Cr2+. Okay. So we want that reaction to happen from left to right. That's a reduction, isn't it? So we want this one to be the more positive value. Okay, so we're going to have to do this one in combination with the top one. Okay, that's the only way that this is going to be the more positive one. Okay. So we're going to combine these two together, but before we do that, we need to make sure the electrons cancel. So we're going to have to multiply this equation by 3. Okay, we want this one to go forwards from left to right, and therefore we want this one to go backwards. So our reaction is going to involve Cr3+ reacting with aluminium. And it's going to be 3 Cr3+ plus aluminium. And that's going to react together. And it's going to make Al3+ and 3 Cr2+. And just check that the charges are balanced here. 3 lots of 3+ means it's 9+. And 3+ and 3 lots, so we've got 6+ here plus 3, so it's 9+ on that side. Okay, And let's just make it clear which one this is. So we're showing the examiner that we understand what's going on. So let's say this is Cr3 plus acting as, well, what's happening to it? It is gaining electrons. It has been reduced, hasn't it? So the Cr3 plus must be acting as an oxidizing agent if it is reduced. Okay, the aluminium has been oxidized, hasn't it? So Cr3 plus acting as an oxidizing agent. Let's just make this nice and clear for the examiner. There's that bit. Okay. Is there anything else we need to write here? So that's acting as an oxidizing agent. And then we need to, it says explain why you've made your predictions. So this reaction occurs because the electrode potential, and we can be lazy here, we can say the electrode potential, just write it like that, of, let's call them by the names, rather than to write this out, let's just call it Redox system 2. That's easier, isn't it? Electrode potential of Redox system 2 is more positive than the electrode potential of Redox system 1. So that's why that reaction happens that way round. Okay. Right, and then finally we then need to do the opposite. We need to find a reaction in which Cr3 plus is going to be a reducing agent. So one where the Cr3 plus loses electrons. Okay. So again, let's just separate this out. And so, right, we're now finding one where Cr3 plus is acting as a reducing agent. So this is going to involve Cr3 plus ending up being oxidized to a higher oxidation state. Okay. So it's not going to involve this redox equilibrium. It's not just going to be this backwards. That would be chromium being oxidized, but it wouldn't be Cr3 plus being oxidized. It'd be Cr2 plus being oxidized to Cr3 plus. Okay. So we need to find one where Cr3 plus is being oxidized. So that's going to have to be this equilibrium. Okay. Cr3 plus is going to be oxidized to the dichromate ion. Okay. So we want this equation to happen backwards. Okay. So if that equation is happening backwards, it must be because this is the less positive electrode potential. Okay. And therefore that must be reacting with this bottom one. Okay. And the other thing is, I mean, looking at these electrode potentials, of course it's these two, right? Because these are by far the two most complicated ones. So of course that's the one the exam board has asked us to do, because that's the joy of the exam board. So we've got to combine these two. It's not actually any more difficult, right? It's just more of it. So we need to combine these two. Again, we need to get the electrons to balance. So we're going to have to multiply this equation by 2, right? And then we want the bottom equation to happen from left to right. And we want this one to happen from right to left. So our Cr3 plus is oxidized. So let's try and copy this out. So we want 2 FeO4, 2 minus. I can't really show you both at the same time. Take my word for it. So it's 2 FeO4, 2 minus. Remember, we're timesing this by 2. So plus 16H plus. The electrons are going to cancel out. And then we're going to have, this has been times by 2. This doesn't need to be multiplied at all. So we'll have then 2 Cr3 plus and 7 H2O. I'm not sure I'm going to fit this all on one line, but we'll try and squeeze it in. So then we're going to go to see this dichromate ion and 14H plus. And then the other products we're going to get are going to be these products here, but this has been times by 2, hasn't it? So 2 Fe3 plus and 8 H2O. Okay. And then actually looking at this, we can tidy this up a bit, can't we? Because we've got H plus ions on both sides, and we've also got H2O on both sides. So let's sort this out, and we'll have 2 FeO4, 2 minus. We've got 16H plus here and 14 there. So that can just go to 2H plus, cancelling 14 from either side. plus the 2Cr3 plus. And then we've got 7 H2O here and 8 H2O on this side, so we can cancel those 7 out and just have 1 H2O on that side. And that makes it look a bit nicer. These have all gone. The 2 Fe3 plus. And then just the 1 H2O, wasn't it? Let's just check this is balanced here. 2 iron and 2 iron. We've got 8 oxygen. We've got 7 there and 1 there. 2 hydrogens and 2 hydrogens. 2 chromiums and 2 chromiums. So we're good. Check the charges are balanced as well. 2 lots of 2 minus is 4 minus. And 2 plus, so that's 2 minus. 2 lots of 3 plus is 6 plus. With the 2 minus means we've got 4 plus charge overall on that side. And we've got 6 plus charge here and 2 minus, so 4 plus on that side as well. Okay, so we're pretty confident that we've got this right. So that's going to be our equation. And then we're going to need to explain this again. So this reaction occurs because the electrode potential of redox system, which one is it? So our dichromate 1 is redox system 5. This one is less positive than the electrode potential of redox system 6, is what we want to say. So therefore this one happens backwards and redox system 6 is the one that's being reduced going forwards. Okay. So the electrode potential of redox system 5 is less positive than the electrode potential of redox system 6. And I think we're done. Let's have a check here. So we've explained what is meant by oxidizing agent and reducing agent. We did that. Predict reactions in which chromium behaves as an oxidizing agent and acts as a reducing agent. Include the overall equations. We've done that. And explain why we've made the predictions. Yeah, I think we're done. We didn't need to write the state symbols, thankfully. Okay, brilliant.